Number 9. So this one you had to do some finagling for sure. Finagling being a technical term for how you solve physics problems. All right, so here's what we know. We know that the canister has a mass of 2 kilograms. We know that the net force on it is 5 newtons. We don't know the direction, so similar to that last problem, we don't know the direction that the force is acting in. It tells us that the initial velocity is 4 meters a second in the positive x direction, and that the final velocity is 6 meters a second in the positive y direction. Okay? So that's our given information. Problems with it. All right, so part A says how much work is done on the canister by the 5 Newton force during this time. So there's 2 ways we could do this. Option 1 is figure out the displacement and then do force times displacement. Okay, and you can totally do that. Like you can do force over mass and find the magnitude of your acceleration, and then do some weird geometry stuff with ratios and stuff. And there is a way to make that work. But what I was hoping you would do is this. So for part A, we're trying to find the work by our net force. So we're really looking for our net work, right? Oh, well, that's just our change in kinetic energy. So if I'm going at 4 meters a second, then my initial kinetic energy should be half of my mass, which is 1, times 4 squared. So my initial kinetic energy is 16 joules. Similarly, my kinetic energy final ends up being 36 joules. Oh, so that means that my work is 20 joules, right? Just the difference between those 2 numbers. Cool? Yes. All right. Now, part B, how much time passed? So I think now we got to dig into the kinematics equations, because those are the only equations that we've dealt with so far that have time in them, right? Okay? So, oh, that's not at all what I wanted to happen. All right, what just happened? Stupid smartboard. Okay, so anyway, so part B says how much time passed. Did anybody figure out a way to do this? Sure, what'd you do?
I found the acceleration because you're given the force and the mass.
Okay, so let's do that. So for part B, our acceleration is net force over mass. I like this. So let's see, our net force is 5 newtons. Our mass is 2 kilograms. So that means our acceleration is 2.5 meters a second squared in some direction. Okay, so now what?
That equals the change in velocity over your time.
Equals change in velocity over time.
So then I just put in the velocities it gave us, divided by the time. I got 2.88.
So when you did change in velocity, did you just do 6 minus 2, or 6 minus 4?
No, I did 6j minus 4.
Good.
I got a vector, and then I took...
Very good. These velocities are vectors, okay? And so when you subtract them, you need to take that into account. Margaret, what were you going to say?
Well, I was going to say that instead of doing like with the 6 out of 6 rate, I just found like the magnitude of it.
The magnitude
The
of,
velocity, like total. So it ended up just being 7.21.
is that like
Yeah.
just the Pythagorean theorem? Okay, so if anybody's not following that, here's the deal. So this got erased somehow because my smartboard got dumb on me, but my VI is 4I meters a second. My VF is 6J meters a second. So my delta V is VF minus VI. So negative 4I plus 6J, right? That's VF minus VI, right? And then what Margaret is saying is now we can find the magnitude of that, right? So this is our vector. The magnitude of our change in velocity, you guys okay with this notation for magnitude?
Yep.
Is, what, 36 and 16 is 42, so root 42, which is, what did you say it is, Margaret, 7 point something? 7.2.
7.2. I disagree. No, wait, it wasn't 7, sorry.
No, it can't be 7.2.
Yeah.
Oh, 6 point, oh, that can't be right. So did I do my math right? This is 36 and 16
It's
Yeah.
52.
is 52.
Yeah, sorry.
Sorry. No, why are you sorry? I'm the one that wrote the wrong number up. All right, so we good? So that's our change in velocity. We know our acceleration, so we ought to be able to find the time, right? So if acceleration is change in velocity over time, then that means our time is change in velocity over acceleration. So 7.2 over 2.5 meters a second squared is going to give you 2.88 seconds. Cool? Any problems? Yeah?
So you couldn't plug into a kinematics equation to find that time? Could you?
Well, I mean, these are kinematics equations.
Oh, my bad. Never mind. I forgot to.
You sure?
Yeah.
Sarah?
For number 2, you said like the velocity of vectors doesn't really matter. So what's the difference between that and this?
For number 2?
Yeah.
Gotcha. Okay. So it's, oh shoot, I'm sorry, Don. So when you're calculating kinetic energy, so when I did part A, the direction didn't matter, right? All I did was I said, all right, to find the work, I got to find the change in kinetic energy, right? And when I found those kinetic energies, I just used 4 meters a second and 6 meters a second, and I didn't worry about the direction at all, okay? Because kinetic energy is scalar, so direction is not important, okay? For part B, we're calculating time using these kinematics equations, which deals with velocity and acceleration. Those are vectors, so there you got to keep track of the direction.
Okay.
Does that make some sense?
I got it.
So the problem number 2, the one you're asking about, is exactly the same as what we did in part A.
Okay.
So direction there isn't important because kinetic energy is a scalar.
Thank you.
Okay. All right. So part C then wants us to find the displacement. So really, you got to separate it, I think, right? You got to find the horizontal displacement and you got to find the vertical displacement independently, I think. Yes. Did anybody do it in one step? Let me see. So what do we know right now? We know our acceleration, but that's just the magnitude of the acceleration, right? So let me see. We know our acceleration is 2.88 meters.
That's the time.
Oh, that's the time. Sorry.
2.5.
We know the acceleration is 2.5 meters a second squared. We know the time is 2.88 seconds. We know that our VI is 4I meters a second. And our VF is 6J meters a second. And we're trying to find our displacement. Thoughts?
I just created the equations for position, and it's the final position, my initial position.
Okay,
I
so
put into vector.
say that again.
I put into like vector quantities for the equation for position.
So so when you say the equation for position, what equation are you talking about? The 1/2 AT squared, or?
No, so you know the acceleration is negative 1.389. Well, you know the overall acceleration is 2.5, but if you put that into vector quantities, 1.389I plus 2.
So how were you able? So this is the crux of this problem. How were you able to get that 1.3 blah 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 whatever you said? What did you do there?
Yeah, wait, what do you mean? Like, I just put into vector quantities.
Well, but all I know right now is this. So how did you split that up into components? I don't know what direction that acceleration is acting in. Now, there's a way to do this, but I want you to be more deliberate about how you got those numbers. What are you thinking, Anthony?
Well, you know that it goes from 4I to 0I in 2.8 seconds. So if you just divide it, you can find your x acceleration. You can do the same thing for the y.
I gotcha. Okay, yeah. So that's actually, I like that better than what I was thinking, to be honest. So I'm going to go that route because I had another way of doing it. But this will totally work. So what Anthony is saying is this, is that if we look along our x-axis, here's what we know. We know our initial velocity is 4, and our final velocity is 0, and our time is 2.88 seconds, right? Do you guys agree that we can find the acceleration? Okay. Similarly, man, now you guys got me. Now I'm not going to say it anymore. See what you did?
Keep doing
Does that make sense, you guys? So this is all. So we can find our acceleration horizontally, which gives you, what did you say that gives you, McKeever? Horizontally, it's 1.38.
3.8.
And similarly, you can find the vertical, which is going to be 2.083 meters a second squared. And so now we can just use kinematics equations and find your displacement, right? Cool? Oh, or for that matter, honestly, I guess you didn't even need the acceleration. I guess you could have just done the infamous Hernandez equation. Right?
That never worked. Like every time I use it.
Right? We know our time, we know our VI or VF. So anyway, so you can find your horizontal displacement. So the horizontal displacement ends up being 2 times 2.88, so what is it, 5.76?
Was that equation infamous?
No, it was. I think it was infamous in my class, but maybe not in Mr. Hernandez's.
It was.
What's 3 times 2.88?
It literally never worked. Like I'm not kidding.
7.96.
8.64.
Dang it.
Okay.
I stopped this stream.
All right. So does this make sense, you guys? All right. So ultimately, it boils down to breaking it up into components. This problem is definitely tedious. So then so that means our displacement is, this 5.76 I plus 8.64 J meters. Everybody good?
Yeah.
All right. Part C, we just did. Part D, now we can find the angle. And I'm going to do the exact same thing I just did. All right? So, for part D, I know that the work is equal to the force times the displacement times the cosine of the angle. So we figured out our work. It was 20 joules. The force was, is it 5 newtons?
Yes.
We just found our displacement, so you'd have to, I guess, find the magnitude of that, right? So Pythagorean theorem it. So you get like 10.4 meters times the cosine of the angle. Does that make sense, you guys?
Yeah.
All right, so that's a new trick that we've used twice today. So maybe make a note of that, that if you're looking for the angle between two vectors, you can use this dot product idea. Sebo, you started to say something and then I interrupted you.
Good.
You good?
Yep.
All right, so that was part D. Is everybody good up to there? All right, and last but not least, part E, all the way back up here. Write the force in unit vector notation. So basically what we need to do is we need to split the force up into components. So remember, your force should act in the same direction as your acceleration, right? So here's the direction of our acceleration. So I ought to be able to multiply by mass,
Yeah.
right?
Yes.
Net force is mass times acceleration. So multiply these by 2, and that gives you, or you can multiply if you prefer, and that should give you your net force. Z, what's up?
Oh, no, sorry, I'm just myself here.
Okay. What else, you guys? Any other problems with that one? That one's tedious. I should probably take that one off the list. Don't love that problem. All right.